Right. So we've got a recording going in process here. So I hope everybody's doing well. I'm going to talk here a little bit, as I mentioned a sec ago, about the project that's on. So to scope this uh, from our original design, because if there was no Corona, we would be at school and you'd have the ability to actually build these things. So usually what I like to do is have you kind of picking something you want to do as a design, build the thing, and then you write up a report, which essentially looks like a scaled down version of a 510K summary. Now, when you do a 510K, a 510Ks are huge. And in reality, no one person should do this. Usually you hire a ton of consultants. There's a lot of writers because it is just a gigantic undertaking to get a 510K in. Um, the summary alone is a huge section. So I kind of outlined the subsections and scaled them down a little bit. So if you look inside the module that's set up for, and modules are when you go into Canvas, there's modules and modules have pages in them. When I talk about the module for it, what I mean is the Canvas module. So there is a Canvas module. I've checked, it's available. A couple of people said they couldn't find it. Um, so if you look on the left-hand side, you'll see modules listed. Click on modules. It should list all the available ones. At the bottom, it should have the module for the project itself. Um, there's four things that are kind of like the uploads and grade portions of it. And then there should be a fifth one. I can't remember if it's the first or the last in the list of them. That's a page that contains like a 2 to 3 page description of what basically I'm looking for in here. Um, so the idea is there's usually a summary in the summary section. There's kind of like what I sometimes call the executive summary. It's usually kind of the intro thing to the whole thing. The biggest thing that the FDA cares about, though, is not often what most people care about. So this is worth kind of noting. You usually put a general kind of friendly introduction to what this is, but then very rapidly you want to get to the point where you compare or tell them what you're going to be comparing. You know, this device that I'm trying to get, through the 510K process, I want to be able to compare it, or I'm going to try to show that I compare it to this other device. So if you remember earlier on, we did the kind of how do you look through and find similar devices inside the 510K database or any of the other databases that are available from the FDA. You find the comparison device, the thing that's closest to what you're doing, and you're basically trying to say that, you're as safe as that device, right? You're showing, that people don't have to worry any more than this other known thing. And by showing that you're basically safety wise and performance wise, at least as good as what's currently out there, then off you go. First, most things are not completely brand new. Normally, we're adding little add-on stuff. I mean, if it's really a completely out of the box type of a thing, that's different, but most aren't. I mean, we're going to be talking about pulse oximetry in the next couple sections here. And when we talk about pulse oximetry has been around for a while, but I mean, we usually say that the first true kind of pulse oximeters that are kind of like what you have today came in the 80s, but you can look back and there's, lead-ins to pulse oximeters that carry the same basic characteristics back in the 20s and 30s. And the pre-ideas of the spectroscopy for it that were just not done as automated as systems were being done in the 1800s when this first, was kind of studied of what the wavelengths of light and the absorption was. So, my point to this is there's almost always a predecessor. So you find what that predecessor is, and in that beginning part, that's what you're going to say. Hey, look, this is the device I'm going to try to compare it to. And very often, what you're going to come up with if your quote unquote new device is something that kind of looks like that, and you're adding it on. Maybe, let's say with COVID, one of the big issues with COVID is, people develop pneumonia, so therefore they don't get enough oxygen. So pulse oximeters are a great way to measure oxygen. There is, Apple watches and all kinds of other watches that actually have the ability to measure blood oxygenation. So, maybe, you want to invent a COVID-19 monitoring device for somebody that's in there. And that you're going to use the Apple watches or some other, watch or device that will interface to a phone, record at regular intervals, and monitor oxygen saturation to determine if this person is at any risk. Right? Just pulling a crazy idea out of nowhere. So, you know, if that was what you picked, then what you and your partner would do is you would go through and start researching on this, finding up how that would work. And you're not going to actually be building it this time, but you should get together enough that I'm convinced you know how you would go about that type of a process. Even if you haven't done the particulars of it, there should be enough detail to say, hey, this is what it is. And I've seen some you know basic ideas of how well you think it's going to perform and what you're going to do. And then for each of those little subsections, you're going to explain what it asks for. So there's a whole ton of these little things you got to go through. How do you show it's similar and what's the operating principle? You have to explain the science. You have to say, hey, what's our engineering design, like a block diagram, and walk me through what's going on here, what has to happen at each of these, stages, things of that sort. So hopefully that kind of gives you some help. So the early stages here that you're going to try to do. If you read through what the book has, the book talks about a lot of the kind of marketing and some of these other um, aspects and how you can look at companies and things of that sort. I think it's very helpful and a good idea to keep in mind. So, I would look through what the book has to say in chapter 28, look through what I put on that page, get a group together, pick an item. You're welcome to email me and say, hey, this is what we're thinking of, and I can give you some feedback if I think that's going to be, easy or hard or anything along those lines. So once you've kind of got that done and you've started to do your research, just keep in mind the sections I'm doing. You might want to just cut and paste that page out into, whatever, a Word document or a LaTeX document or whatever suits your fancy. And then you'll go through and just start filling it in as you do your research. I gave you rough ideas of what I would expect the page count to be. It's not a magic number, but it should give you a pretty good idea space-wise. Um, I don't want you to overshoot that a whole bunch though, because I don't want you to kill yourselves. I want you to try to think efficiently. What can I get across here? All right. So that's kind of my quick overview. Does anybody have any questions about the project? Say, I see hand raised. Yeah, just
Am I on? Can you hear me?
yep, I can hear you.
Awesome. So just making sure, whenever you say we're going to pick a device, we are the ones who are conceptualizing a novel device. We aren't going out and we're not going to go pick a pre-existing device. We're going to come up with something ourselves.
So kind of yes with an asterisk.
Okay.
What I would suggest is pick a device that's not too complicated, that you can understand. Either we've talked about it here, or you can go out and you can look and find something that's reasonable device. I'm gonna mute you for 1 sec, just because I'm getting a lot of feedback. And if you have more questions, you can unmute yourself. So what you're going to try to do is, all right, there we go. You're going to try to pick a device. Like you could go out, I mentioned the idea with an Apple Watch, right? An Apple Watch actually it actually uses green light to monitor it because it's a little bit better for reflection, but I'm not going to, don't sweat that detail yet. Let's say you just decided, hey, Apple Watch can measure blood oxygenation, and I want to use that to build a monitoring device on an Apple phone. I'm sure you could do similar things with all kinds of other devices too. So I'm not trying to say a particular one, but just imagine you pick that one. So you've got an existing device. What your value added to this would be, you're saying, I'm going to, supposedly make an app, and you imagine you've made that app, and you're going to block out what would you do to make that app, but you're not writing the code, you're not developing all the details. It's reasonable for you to say, hey, look, I could, ask the Apple Watch to send me a monitor at regular intervals of what the blood oxygenation is. And so you send out a request to the watch to take a measurement and send it back to you. Um, so that would be the kind of the basic idea, that you could take an existing device like that and do a small delta to it, right? Adding an app to put regular monitoring in to then check kind of progress of COVID. And you could also monitor the person's temperature, right? Because people run fevers and things like that. So from standard biometrics available on the phone, you could measure a couple different things that were COVID active. And, if a series of these things hit on whatever is medically interesting, you would raise a flag. You don't necessarily have to know all the details of what's medically interesting for that. Um, I'm giving you a little bit of leeway. This is why I say it's kind of like a simplified version of a 510K, because you're not able to build it and you're not necessarily the greatest expert on it. But you would look at it and say, hey, look, I know fever is an issue, and you can cite some sources on that. Um, how high of a temperature, you just say, a threshold of, T for a period of you know, temperature T for a period of X hours is dangerous or whatever. And you could just set that with variable values in it. So you don't have to per se say, and you'd say, so I would set an alarm for if, the person's temperature has been over this value, or if their oxygen level drops below a certain percent for a certain period of time, right? So you could decide that. Now, these are just some ideas off the top of my head. You could decide, hey, look, I'm interested in prosthetics, and I want a prosthetic that's going to do EMG measurements on an arm, and it will actually then actuate a prosthetic device so that we can sense from the upper muscle, we should be pulling the lower arm up. The lower arm's now a prosthetic, so we can actuate on that. And you can say, hey, I would use, an EMG to do the measurements, and I'm going to be doing muscle wire, for instance, as the actuator to pull it up. That would be another way that you could take something that are some existing devices, EMG, muscle wire, things of that sort, um, basic prosthetic design to make a prosthetic that would then act like a hand. Does that help?
That makes a lot more sense.
Awesome. So, again, just think of it. The reason why I think some type of an initial device is kind of like a baseline, it just gives you a lot of stuff you can read and you can research, you can gather data on. So you're not just making stuff up out of the blue. You're able to collect reasonable information that will form the basis of a lot of that. And you can take pictures from it, and you can then take some of their data, and then the delta parts would work better. All right. Any other questions?
Dr. Schubert, I have a question about the final presentation.
Yes.
Would that be the form in, I know we're going to have our own screen. So are we supposed to make like a PowerPoint or just same thing as our the document or the page we're turning in, and kind of just explain it with our own screen or different form?
Great question. Okay. So I would not suggest using the document you're turning in. You're going to pull information from the document, but if you've ever seen somebody present a document, and sad to admit, I did this during my PhD or master PhD. I think I actually presented a paper. It was like the worst presentation I ever did, because there's so much text on the page. text is really tough for people to deal with. You show somebody like projection of like an article page, and people see that much text and they just start zoning out on you. Or even worse, they start reading and they're not listening to you. So I would never suggest actually putting up a projection of the paper. So PowerPoint is a very reasonable way you could go, or any other similar type of presentation software you want. But you notice right now, we're going to use this same exact platform, WebEx. You can turn your camera on, and what I've done, I've just taken, this is one of those cheap, like $5 whiteboards, and I just put some sticky stuff on the wall and stuck it up on the wall. Um, you know, so that I had something that I could present on, and then, you know, this is in well, it's actually in my laundry room actually. Um, but almost nobody's coming in. So since my house is really dense right now, it's like the quietest room in the house when the laundry machine's not running. So that allows me to have access to it. You'd be welcome to do this too, where you could share your screen, everybody else would turn the videos off, and we could just watch you presenting, and you could show whatever you want. I think most people are going to feel more comfortable with PowerPoint because you're able to show pictures and things of that sort. Um, PowerPoint's great when you want to show something that would be difficult to write, number one, and number two, you're not expecting people to take notes. So I tend to try to avoid PowerPoint for an interactive thing because PowerPoint is very difficult for most people to take notes on. And um, when I'm writing things, I'm trying to show you what I think is really important on and try to show you key features of it. So probably I'd say about 99% of people in the past have done PowerPoint. I've had maybe one or two people over my whole career who have done video, but hey, maybe you love that. I'm not going to say no. So, but yeah, PowerPoint's probably the best. Does that help you?
Yeah, that helped a lot. Another question would be, there's a project proposal under the entrepreneurial projects page. If we put that in like right now or within this week, would you give us feedback on
Yes,
what we're about to do?
that's there for. Yeah, that's so that you can put in enough information so I can figure out what you're doing. I you know, page or less, maybe even just a paragraph. Um, it could be a picture and a little description or whatever. Like if you like let's say I was trying to put in a proposal for that Apple Watch thing, right? I mentioned, say in a paragraph, I could say, hey, look, Apple currently has a watch, integrates with its phone. My plan is to, you know, work on an app that would be interact with it. And again, work on an app doesn't mean you're actually going to build the app. You would just be telling me how you had theoretically built it. Right? This is kind of hypothetical. There's not enough time or software for you to develop it in reality. But you could then say, hey, look, I'm going to build that. And that way I could look at it and say, okay, Apple Watch integrating with an iPhone and measuring these things, plotting some alerts, things of that sort. All that seems like something reasonably they could research up. And that can give you the big thing I'm trying to give you feedback on that is, do I think it's a realistic one? Some things might be too simple and, therefore, kind of really honestly boring. And some things might be too difficult and take too long. So that's kind of my goal in that. Does that make sense? Awesome. Any other questions?
Yeah, so PulseOx, it says you're doing a WebEx over that soon, next Tuesday.
This right now.
Now? Okay, it says near
This
infrared.
is on WebEx. So that as soon as we're done here, I'm going to talk about the theory behind a pulse oximeter.
Okay. It says today's near infrared spectroscopy, so I was just
So near infrared spectroscopy is the scientific theory behind a pulse oximeter.
Mhm.
So near infrared spectroscopy can apply to a large number of areas. A pulse oximeter is a very special case of doing nears.
Okay.
So the general theory is nears, and the particular application is a pulse ox.
Okay. And then
This is kind of separating the science. And then my plan is next week, I think it's Tuesday. My plan was to try to do one where we're actually kind of walking through a build on this. So there's a couple things I'm doing. I've been kind of back and forthing whether it'd be better for me to pre-build it and walk you through my circuit or whatever. But yeah, but the next several things are going to be all based on pulse ox.
Okay. And then will the lab report be due after that? Pulse ox?
Yes.
All right.
Yeah, I'm going to be somewhat flexible on, lab reports and the rest of that, as long as I get them in on time, because it's kind of screwbally for both of us at this moment.
Mhm. And you said there'd be possible assignments or quizzes over the like pacemaker and
Yeah, I have to do one for, I've been contemplating combining that together with the stuff for doing blood pressure and that, kind of doing a kind of heart overarching one. Um, so to, that I'm hoping I should get out by the end of this week, and then I'll probably use the report on the pulse ox as all of the measurement for the pulse ox. And then we'll have some stuff on like EEG and some other cleanup stuff, which I'll probably make. So probably two quizzes, one on all the heart related stuff, and then one on everything not pulse ox. And then pulse ox, I'll grade you based off of what you turn in as the lab report.
all right. Thank you,
I
sir.
don't want to put too much in just because from watching, I've got a son who's at Baylor, and it takes him a lot longer when he's doing it at home versus when he was actually at Baylor. So I'm trying to be sensitive to that timing and figure out where that line draws. But I think that will be a reasonable amount, that I'll get a good feel for whether you understand the concepts. Hopefully give you a chance to check if you understand the concepts, without causing undue stress and strain.
Awesome. Sounds good.
All right. Any other questions?
Yeah, for I think on last Thursday there was a page that said there would be like blood pressure videos posted, and I haven't seen them. So I'm wondering like were they posted, or did I just miss where it's supposed to be?
The uploading of the videos is taking much more horrendously long than I anticipated.
Okay.
So once videos get sufficiently big, so I'm trying to cut the videos to make them uploadable. So normally when I've uploaded videos like this in the past, I've been at school where I've got a really big connection. And right now I'm in a house with a bunch of other people who are, unfortunately, I've got, a ton of people doing classwork and things of that sort. So I've got 4 kids, and then we actually have a Baylor student who wasn't able to go home because they didn't have enough bandwidth. So so I've actually got 5 people doing student stuff, and my wife teaches. So there's like 7 of us gobbling bandwidth, and upload speed is really slow. So what I've noticed is when I try to upload it, it gets partway through, and then Kaltura kicks me out and deletes the whole upload.
Oh,
So
okay.
I've discovered if I can cut them down to shorter lengths, it seems to be more likely to finish, and me not to want to curse them and their whole families and stuff. So, so I'm currently trying to get them into a reasonable size length and upload that. Yeah, sorry about that delay.
Okay. And also, before the break, he said that our ECG report would be due immediately after the break, but of course, like things changed, so I was wondering, what we're gonna do about that.
So I've talked to the grader who's actually doing the grading of it, and I just told her, hey, look, give them time, let them upload. So, it's basically the same type of report as you would have done for the EMG. You're just doing for the ECG. Upload it when you get the chance, and she will grade it. You know, so that you don't kill yourself. I'd try to make it pretty quick here, but you should have enough. Does anybody not have what they need to be able to do the report? I'm guessing that means everybody has.
You remember what was that database called? That you showed us
You need a link to the database and all that.
The VisioNet. I couldn't download those files to do the waveform smoothing.
Okay.
They all downloaded as like .mat file. Not that. It was kind of file is this? Yeah, .dat file. And
Yeah, so they actually give you an option when you're downloading. Pick different ones.
Okay, I must not have seen that.
What I'll do is maybe I'll download myself and then make it available.
That'd be great. Awesome.
Would that help everybody? Is that the kind of limiter trying to find that file?
That was a limiter for me at least. But that'd be great if you could make it readily available.
Awesome. I should be able to do that. All right. Any other questions? All right. Well, I think we got a lot done, at least on that. Now we'll move into the kind of next stage where we're going to talk about near infrared spectroscopy. So the basic idea behind near infrared spectroscopy is if you take a look at shining light through, you know, I don't know how well this, I put in like a light, I don't know if you can see, like when you shine a bright light, hopefully that's not blinding your screen completely, through, you can see my fingers kind of glowing, right? Because the light is passing through. And what you're noticing is you just see the red. And that is because of the blood, but it's not actually as much as you might think on this. So it's a little different than first blush. And the difference is that not all the wavelengths of light penetrate through equally. So if you plot the percent absorption, right, and it's based on a distance you've traveled, but let's just worry about the percent absorption, right? And you plot versus frequency, right? So 660 is like the end of red. So if we have the visible light here and we're going into the infrared portion, for most of the visible light, your skin is completely opaque. That's why people can't see through. But it turns out that once you hit about 660 into the near infrared, it drops down really low and then it kicks back up again. So this is kind of an oversimplification. We'll draw in some of the details in here. But this portion here from just above red, kind of that 660 zone, up to about 1,000. These are all in nanometers, right? This area is called the near infrared. And it turns out that there's actually a very low absorption. So it goes from 100% down to, for certain things, less than 1%, you know, per millimeter. So it's a fairly low value. So we call this the near infrared window. Now, you might think it's so low that it's like completely translucent. It's not. It's kind of, they're more like watery milk or muddy water type of thing. If you've ever taken like some, you know, milk, add a little bit of water so it's kind of diluted, but you still can't see through it, and you shine a light through it, you'll get a lot of light will travel through, but you can't completely see, but you can see brighter sections where the light is. So particularly if you do like a little LED behind it, you'd be able to see it carry through. Well, that's the idea, but it kind of scatters outward. Right? And the scattering on that is a Gaussian scatter. So the further in, so if this is kind of the entry area and you've got your light source that's shining, you initially would have a very bright beam and it's gonna scatter, right? So those photons coming in, some of them are gonna scatter in different directions. So you tend to get this kind of, spread out areas. The light goes further and further and it gets dimmer and dimmer. That's actually what's happening as you're going through this window. This is just enough to scatter and make it milky, but to allow it to pass through. And then depending on how concentrated things are, that will actually affect how big this level is. So that's kind of the first observation that made people go, oh, we can see something through here. So maybe we can tell a difference by what's going on. So let's take this and kind of expand it out. Now there's several different ones in this near infrared window that are actually able to have some type of reaction, show things. The first is kind of like deoxyhemoglobin. So for deoxyhemoglobin, we're looking at, so this is the carbon dioxide on hemoglobin instead of oxygen. And it goes down, then there's a little upkick, and then it comes back around kind of like that. Actually, no. It does that eventually. Let me, it goes kind of down. I need to show it wide enough so you can see the crossover. So this one is the deoxyhemoglobin. HB is what we often use for hemoglobin. So this is sometimes also called reduced hemoglobin, if you ever see that term. And I probably should have done that one in blue or something. Let me know if this, I'm gonna try to do a different color for the next one. So the next one we're going to take a look at is actually our oxyhemoglobin. Now, it dropped a little bit faster at first. It kind of crosses over. This crossover point is at 805 nanometers. Can everybody see the red line? You can type text. I do have the chat window open. Okay, I'm seeing, yes, we can see this. Awesome. So this one is kind of the oxyhemoglobin. So those are the two ones that we're going to be really interested in. Now the other two that comes in, I'll draw them both with purple. One is carboxyhemoglobin, which kind of comes down like this. And so it has very little effect. When you're looking through it, so we can essentially, and it's not very common. So therefore it's, basically a very low factor inside here. And so we can essentially neglect it as noise. The other one we're going to have to deal with is going to be our methylhemoglobin. And drawn this one almost too high because methylhemoglobin's got to go even higher, but then it carries down. Maybe let me modify this, showing kind of a bigger section. They have to cross over, but in any case, this is right. So this one is the methylhemoglobin. So it's potentially in the mix, but its concentration is low in anybody who's healthy. So if you're doing kind of regular breathing, this has a very small concentration, right? So that's not actually a proof that it is, But if you're walking around and you're healthy, then that's low. So because there's very little of it, even though it could absorb, there's not enough of it to absorb. So that kind of gives us, essentially the ones that are in purple we neglect, both because of low concentration and in one case also low absorption to it. So that, the only ones we have to worry about is our deoxyhemoglobin and our oxyhemoglobin in most cases. So these are all called chromophores, chroma color, right? So the idea of this is these are the ones that in the wavelengths we care about that are going to give us some type of reaction. So I'm going to remove the purples because we don't need them. Because essentially we can say, ignore them. Now, there's one other interesting feature about this chart for us, if you notice. That to the left of 805, deoxyhemoglobin dominates. So if we were to measure somewhere over here, say like 700 nanometers, and then we were to measure somewhere over here, say, 940 nanometers, you would have kind of them flipping their place. Now, each one of these, right, what we're plotting here is basically a coefficient of how well they can extinguish. So this is often called the alpha coefficient for it, the extinguishment coefficient. And when we look at what's called Beer's law, so Beer's law said that the intensity of light that is transmitted through a sample is equal to the initial amount of light that you have on the surface, and then it's going to depend on how much is absorbed. And the amount that's going to be absorbed will depend on how thick is the sample it has to pass through, what's the concentration of the sample, and let me write these up here. Distance traveled, concentration, right? Our extinguishment coefficient, and we're going to take e to the minus all of this, right? So basically, if you've got more of the stuff, if the stuff absorbs more, if you have to pass through more, right? All of those are going to effectively, right? This is a negative exponential, so it means you're going to get a fraction passing through. It's an exponential law, which means the relationship between these will be logarithmic. So we often say there's a logarithmic relationship between what those light intensities are. Right? And it's this thing, which is Beer's law, kind of forms the intellectual basis. Well, on this side, deoxyhemoglobin dominates. So if I were to look at a combination of these, I'd have for the deoxy, and then I'd have a second term absorbing at 700. So this would be the intensity of light. This is all at the 660. And I'd have the intensity of light at 660, right, 660, minus, again, distance, concentration, but this concentration is going to be deoxy versus oxy, and alpha of the oxy. Right? So essentially you have absorption for each of them as a sum. We're not going to actually have to calculate using this, but I just want you to understand how it relates on these. So I can take, basically how much of the light is passing through. It's going to get absorbed by both of these. I have to be able to separate them. Right? Since this is just times I0, I can factor that out, and then it just depends on what these values are. So usually what we do is we would divide by I0. We have how much was transmitted over how much was initially sent. So that's the fraction of light we're dealing with. And then if we took the log of this, then we'd have this equal to minus d D0 alpha, right, for the oxy, and minus DC deoxy alpha deoxy. The distance is the same. I could technically do a 1 over D to get rid of that because the sample amount is the same for each of them. I could also leave it there if I wanted, but you can imagine I could do that if I really felt like it. And then I've just got a simple little equation here for these. Right? Actually, let me leave the D back in just because we normally leave D here. I'm going to erase this because I need a little room to kind of extend this down. And hopefully the idea of this chart. You can look this up if you want on the internet. If you go to Google or whatever your favorite search engine is and just type, infrared, or, NIRS, NIRS, and say wavelengths or something of that sort. It'll give you this picture. So I've got my log of these, right? This is just appended. So this log of the transmitted over I0, and this was all done at 660. Has to be equal to, I'm going to write this in matrix form, minus DC the oxy, and minus DC of the deoxy. And then we're going to multiply it by alpha of oxy and alpha of deoxy. We have a matrix equation that we can then write. Basically, we've just turned this combination together into a matrix equation. I've done this at 660. I can do the same exact thing now at 940. I measure the intensity of light that goes through and how much I sent at 940. Get that ratio, take its log, and I can get that that will be minus DC oxy. Again, same values. Deoxy. So I could technically take these, right? What are each of these values, and I could calculate them. Now these alpha values that I'm doing, I can actually split them, right? Because you might look at this and go, oh, I'm going to get, right, this alpha coefficient that's on here. Well, this is how we can initially measure what the alpha values are using these equations. If I were to take this alpha in, I'm now going to flip it with my concentration. I put the alpha here. So doing it with the alphas there, I can measure the alphas. That's the initial science area. Then we flip them, and we now take a look at the concentration of oxy. Because now, once we've done the initial measurement, we know what these values are. That's what that graph was. So that initial equation with alpha pulled out, let me measure this, calculate the alphas, and away I go. Then I can come back here and go, now I pull my concentrations out. That's O. This one is deoxy D. I do the same thing here. So I just rewrite my equation slightly. Concentration deoxy. And the reason why I want to rewrite them once I go to try to actually do a NIRS or to try to do a pulse oximetry measurement. Doesn't matter, we're doing log and stuff. So when I'm writing log here, remember all logs are equivalent. So my statement was I'm picking, I was doing 660 and 940, I think. But it doesn't matter. You can pick any ones along the line. What you have to do is once you've measured your alpha zeros, which has actually been done and tabulated for you, you can actually pick any value. So people will often pick for this one, anything bigger than 900 is usually good. So you'll see people, common values are 910, 940. See, I think there's 960, a 970. And what these actually correspond to, these choices, are not something magical on here. It's usually these are the ones that you can cheaply get LEDs that have that as their peak intensity. So it's really more based on available LED values. And so the similar for the 660 is pretty common because it's red. So if you buy a red LED, it's really good for doing this ratio up here. But you can do something that's just inside, 700, 710, 720 are pretty common values they're used. I've seen 740. So again, for this one, it doesn't exactly have to be here. All you have to do is go to those, the graphs, or you can pull up a table that has at different wavelengths what the extinguishment coefficient is, and you put them in. And we're going to show how we can even bypass this, the need to measure those at all in a sec. But this is just kind of the first cut of it. So we did the first thing with the alphas out to measure the alphas. We made the charts. Now we pull the alphas in and we pull the concentrations out, because in a person, right, when you did the first measurement, you would have known concentrations. That's how you calibrate the curve, right? So you take something and you can put a certain ratio of oxygen into it. So you calculate the partial pressures and you just measure the amount of gas partial pressures, which tells you related to what the actual amounts are inside. So you can generate these curves. That's it. And you can therefore measure it by some other means, like, usually some type of a chemical means to be able to get the equations. And so from the first equation, we got these and we just swap them. And now we've got the concentrations. Well, these look pretty darn similar. The only difference is this is going to be alpha zero measured at 660 and alpha D measured at 660. Because remember, alpha varies by frequency. And this is alpha zero at, I'm using 940, and alpha deoxy at 940. So these values will change slightly. But now I can say, great, I can combine this into one big lovely equation, right? Where it's CO times all that and CD times that. So I only need one of these two. And I just stick this in a matrix. And I can measure these values. And the distance I can measure on somebody's finger. And I can actually put in these extinguishment coefficients. And then I know these because I measured them. And I know these because they're, D is measured and alpha zero comes from a table. So now I can get C0 and CD, the concentrations of the oxy and deoxyhemoglobin, which is what you want. And when we're taking a look at your percent oxidation, we're taking a look at what is the concentration of the oxy over the total, oxy plus deoxy. I keep not wanting to write that C. So that's what we're looking at as our ratio for this. And for a long time, this is what happens. This is the way people measured it. Because it's a straightforward thing. It's a matrix calculation, but it's a 2x2. So there's actually a closed form solution to this. So, you can plug in your values and away you go. The only difference is this D, but it appears everywhere. So I can pull the D out if I wanted to. And that's why I said sometimes you see the D over there, sometimes you see it over here. I could pull the D out of here if I wanted, and I could scale this side. Or I could do 1 over D, and then all my measured values are here. And then the alphas are the kind of taken from a table in advanced values. And so I just invert that, multiply, and I would get my values of C and D, stick it in this ratio, and boom, I've got my oxygen. Multiplied by 100, and now you've got a measurement of what is the percentage. And that works really awesome as long as all of these values are straight on. And as long as you perfectly know what the initial intensities coming out are. Now, over time, your lights are not going to produce the same amount, right? So this works, but it's got some problems. So we're going to talk about what the problems are this way, and then we'll talk about how we can do this even better by strangely doing less work. So you can imagine when I hook something on here, there's a chance for things to vary a little bit. You know, number one, I could be squeezing my fingers, so my Ds are going to be pretty hard to tell. Second off, this D, it's not like your finger is one constant thing, right? There's bone in there, and there's flesh, and there's blood. If you squeeze it too tight, you have less blood. Right? So there are a lot of variables that do kind of come onto this. So, you know, D is hard to measure. Since there can be different materials, you actually have a blend of different extinguishing coefficients. There's one for your blood and one for tissue and one for bone. So this starts to kind of break down a little bit. You can say most of it's going to go travel around the bone, although your bone is translucent also, and things of that sort. So you kind of look at this and go, oh, wow, that's starting to get ugly again because I'm going to get more coefficient, which means the matrix grows. Now I could do a whole bunch of different measurements over time and try to tease things out. But as time goes on, the longer you run this, the intensity doesn't stay constant either, right? So the intensity of what your light is, as it warms up, more electricity has traveled through it, right? It's not going to have the same exact efficiency in producing light, which means these I zeros will drift. So all of this creates a lot of variables. So this is a good approximate equation, and it can work, but you know, it's got some issues, right? Drifting values here, right? You know, the distance, not always quite the same. There's actually a whole bunch of materials, so it's really a composite of these. Not so easy to pull out anymore. Concentration of CO is the concentration of the oxyhemoglobin. And CD is the concentration of deoxy. And concentration is telling you how much in the blood. So how much of your blood is oxyhemoglobin versus deoxyhemoglobin. If you're getting a good measurement of blood flow right from the heart, it should pretty much, if your lungs are doing what they're supposed to do, it should pretty much be all oxyhemoglobin, right? Because the lungs, if they're operating correctly, have gotten rid of the carbon dioxide and have pulled in the oxygen. The reality is it's never perfect, and there's been some exchange between your heart and here with other things, because not only do you have arteries, but you also have the blood vessels, you know, the veins returning things back. So there is a mixture of them. But the concentrations tell me basically how much oxyhemoglobin, how much deoxy. And in general, we would like to see that ratio really high, upper 90s. Right? That means there's lots of oxygen for your tissue. If there's not, then you're actually going towards a hypoxic state. You cannot survive if that drops, you know, too low. You're from most of the stuff I've seen, people can live in the 90s, but you start getting some hypoxic conditions in the low 90s, and like 96 is no problem. But if you get into kind of the low 90s, high 80s, you're looking at somebody who doesn't have enough oxygen, so they tend to be trying to breathe heavier. And if I remember correctly, I'm not going to claim I'm a doctor, but I believe it's you know, somewhere around low 70s that people die. So that gives you an idea of what that ratio, about where we're looking. Does that help? Yes, awesome. Okay, so I can solve this matrix for these concentrations, calculate it, away I go. You know, and that's nice and all, but like I said, there's some problems with how they drift and how they measure them. So we want to try to figure a different way that's related to this. can account for some of these other issues. So if we look, there is actually a little bit of variance that goes on with your heart beating. So if you watch when your heart beats, so let's imagine here is our oxygen saturation in your blood, and this is now time, not a wavelength thing, just time inside here. When your heart beats, it pushes out really oxygenated blood, so it's high. And then, say this is at a heart pulse, and this is your next heart pulse, and the next heart pulse. So these are the, heartbeats. And so at the next heart pulse, I'm going to be high, and at the final one, I'm high also, right? But in between, the blood has been pushed out. It's exchanging now with the tissue, so you expect it's going to drop a bit. And then it'll actually get pretty low, and then the next pulse is going to come in, and it'll drop off, and then the next pulse comes in. So you kind of see this up-down wave that goes in from what I'm getting the really oxygenated blood from the heart to where it's been kind of sitting in the blood vessel. And it's not very long, because remember, you're beating, say, 70 beats a minute or something of this sort, maybe 80, something like that. Could be 60. Anyway, somewhere in that 60 to 80 zone. So you're talking about, a second or less between these. But as it's sitting there, there is going to be some exchange, and you'll get carbon dioxide out of the cells, so it'll drop down. Now, this is what's happening on the heart area. There's also other things that are absorbing things in here. So, that's carrying in. If you looked at the extinguishment, so if I plotted the extinguishment coefficient, the net one versus time, it's going to look pretty much the same. And so this is saying how much light is absorbed. But it turns out, so this is caused by the blood and the changes, right? At the peak oxygenation, at the peak amount of carbon dioxide before the next set of fresh blood comes back in. Well, there's also, it's not right around zero going on here. So on the extinguishment, so that means there's something also extinguishing things down here that's causing the bias. Right? So the extinguishing coefficient is doing the same basic thing as the saturation, and that's kind of a nice feature because we can relate them. And the extinguishment coefficient, this height here, which we often call this part down here the DC part. Technically, DC should go to the middle, but that's not how we do it. And this is our AC component, right? The oscillating up and down, difference from peak to trough. So when we take a look at this DC component is made up of the absorption. Your tissue is at a pretty constant level of oxygenation and absorption. So there's absorption from tissue, and bone and blood vessels. And this is the blood here. We don't care about this part. Some people might care about this part, but for pulse oximetry, we don't care about this. Is an inconvenience. But I can find it all by the DC component. So if I measure it over time, which we did on that first one, I had no time component. I just boom, snapshot, solve the answer. We could say, well, look, I can look at this, and I can, all these things that were creating difficulty with my distance and the mixture of things and everything else, I can remove. So I can take a look on these, and I can measure. So if you plotted, I remove the saturation here for a sec. If I were to plot, right, for two different wavelengths, I'm going to put red for my red light. So you can imagine I've got my 660, and it's going to be doing its ratio, And further in, maybe I've got my 940, and let's just say for the sake of argument, it's just a little bit above it, right? A shifted and displaced version. Well, some of this DC value could also be how bright the initial light was. So if I took this and I said, okay, what's the DC value of this blue? And what's the AC value? And I took the ratio of the AC value in blue over the DC value in blue. And similar for the red, I found out what was my AC value and what's my DC value, and I took its ratio. So by calculating these, I'm kind of using the DC value to scale the AC. So that'll take care of, things that are being absorbed and how bright were the lights. I'm only looking at the varying part because that's what I care about. And I'm scaling it by how much light has reached it. So it doesn't matter if the light was dimmer or the light got absorbed by a whole bunch of these other layers. I basically want to remove all that effect. Well, by dividing by it, I'm essentially dividing by the amount of light that actually reached the blood. If that makes sense to you, right? So dividing here, right, by the DC value is in essence, assuming this is modifying my I0. So I'm just measuring I0 IT for the amount that's passing through the blood. Okay? So that ratios now give me the ratio of what I've got for each of these frequencies of light. And I'm really now, there's no longer all the other tissues and everything else have been removed. So I'm just dealing with that portion. All right. Sorry, my board is small and I want to keep that part. So if I've now got these, values that are ratios here, if I take the red one and I divide it by the blue one's ratio, this is what we call R. Right? R is just means ratio. So this is the ratio of how much of the red variation over the red bias and divided by the variation in the blue over its bias. And we're assuming the variation is basically caused by the heart. You should see these regular pulses. Okay? Now, when we take R, if we were to plot R versus SP, well, right, SpO2. So the saturation of oxygen inside of your blood. If we plot this versus R, 100% oxygenation happens basically at a ratio of 0.4. And you have 0 at about 3.4. That's about the range that you've got for these. And 1 is about 85%. It's a fairly straight line between 0.4 and 3.4. There's a little bit of curving at the top and a little bit of curving at the bottom, but not really a significant amount to go. And this is kind of the range we're going to expect most human beings are going to be operating inside of. Because if you drop below 85, you're in serious issues here, where this is, oxygen deprived distress. So we would expect this ratio to carry in here between 0.4 and 1. And so now we've got 2 points, we've got a line, so we can actually convert from R to the oxygen saturation just by using a linear approximation between 0.4 and 1. And it will extend, so you can go lower if you need to. But it turns out this is a much better way because it removes a lot of those unknown variables. And if the light intensity changes, as it, warms, you get less light out or something like that, it's less efficient. The whole curve drops, which means DC drops, which means it's going to automatically get accounted for. So light variation intensity doesn't matter. We've now removed all the tissue stuff. We just removed huge amounts of our problems that are on by doing this time measurement that's going on. So we have to do a decent number of measurements, right? It'll take at least a second or so to be able to get this because we have to calculate an average between these pulses, right? Or at least peak and min. So you need at least one heartbeat to be able to do that. As an added bonus, since we're measuring over time, we can find out when the peaks occur and the time between here, 1 over that time. So this is our time t. So 1 over t is going to give you what your heart rate is. 1 over alpha. 1 over t will give you your rate that your heart is beating at. And you can, every time you hit a max, you can flash an LED to get that neat little heartbeat. Boop, boop, right? So every time it sees it, and all you have to do to get the max is you just smooth it slightly. So you put it through a slight low pass filter. And then once you put it through a low pass filter, it's a little bit smoother. And then you just come in here and keep measuring as it's getting bigger and bigger and bigger. The second it gets smaller, you flash that heartbeat light, right? And that gives you the beats, and that lets you know the minimums, or sorry, the maximums. The minimums you just do the other way. As you're going down, the second you go back up again, you flag that the last time interval as basically when your minimum was hit, and you take that value. And that gives you the difference between those two, gives you AC, and that one gives you your DC. All right. So, this is basically what's done on most pulse oximeters as a basis thing, right? Simple thing, 2 frequencies of light, measure it over time, find the max, find the min, calculate these values, calculate ratio R, and then use this calibration curve to go from the value of R to the value of the oxygen saturation. And we can calculate other things like heart rate and things of that sort. All right. Do we feel comfortable with this? I might have put everybody to sleep pretty good. Okay. Good. What is E? I'm trying to find where I don't have an E up here at the moment.
Is it 1 over t equal to, I couldn't see what that.
That's rate, R-A-T-E. It's your heart rate.
Okay.
Right? So if you calculate the time, the peaks happen when the heartbeats happen. Right? So this, if I were to plot your pulse, you'd have, P, U, R, S, and UT comes in, right? So the QRS complex happens just before. There's a little delay between this, where the center of this is, which is the time for the blood to flow from your heart to your extremity, wherever you're measuring it. That's not too long, but there's a little delay. So if you imagine this, which is doing the pushing the blood out, there's a little delay to it. You've got your relaxation here, diastole, and then it starts again. And there's that same little delay here. Right. So basically you're measuring the heartbeats are just a slightly delayed version of what you're seeing in the pulse oximeter, but that means the distance between this is the same as the distance between these peaks. So therefore, if that's the time between the peaks, 1 over the time is the frequency or the rate. Right? So your heart rate is 1 over the time. That's all I'm saying with that. Is that okay? So the nice thing is I can get a lot of different stuff out of it, right? I can get heart rate. I can, actually see different characteristics. The shape of this curve will tell me, some information about how your blood is flowing. Right? It spreads out. It'll be more peaked closer to your heart. It spreads out more as you get more to your extremities because there's time for the wave, right, to kind of spread. Yeah, so there's a lot of things you can actually read out of this, but the first of which is our concentration of oxygen, which is a big issue for us. Okay, good. Yes. Okay. So this is pulse oximetry, and it's based on all that near infrared stuff we mentioned there. We've got like 2 minutes left. I just want to mention a couple other things that can be useful in this, because I don't have to just do this on a finger, right, or on an ear, right? You'll see some that are ear clips for pulse oximeters because, your earlobe is actually a pretty good measurement spot. Your forehead's used a lot for reflection, so certain frequencies will penetrate through skin but won't penetrate through bone. And so this is why green is pretty efficient, because green will go a little bit through the skin, but it won't go through bone very well. So people will actually do reflection versions of pulse oximetry by putting a sensor on the head and bouncing them off. That's essentially what's being done by the watches too, because you've got bones in there. So they're bouncing it off the bones back to the sensor. And so very often green is picked for the reflection versions of these. Another one that's often done is we can put these on muscles to try to actually measure. We tried to throw away the tissue variation here because we're concerned with the blood flow, but I can actually try to actually find that BC value, which is going to tell me how much of the oxygen has made it into the muscle. So that's going to tell you how efficiently the person is able to transfer what's in the blood into muscle tissue. So it's often done for therapy stuff or for athletes to measure oxygenation inside. They usually have, the two sensors that are done reflection style. They don't do it red because they don't want to bounce it off the bone and it's too thick to go in. Light will only travel a maximum of maybe 5 centimeters before it gets lost. So, very often we do a reflection style, but we do red. And what happens on those ones, if you imagine this is the skin surface, and we put an emitter, and we put a detector, right? This is traveling out. So the detector will see some. What happens is the path of light getting there kind of does this. It travels, and it follows what we call a banana curve because it's kind of shaped like a banana. So you'll measure part way in. And as long as the main bulk of this is inside, say, whatever you're interested in, maybe you got skin and maybe you got muscle there, you're good. But this is often used for near infrared, and you can place it all over. It's also done, so this is one of the research areas I work on, is you can put them all over the skull, and since infrared will travel through bone, the 5 centimeters will go deep enough into your head to actually reach the outer layer of your brain, just barely. So this part right here would be your gray matter, white matter below it, gray matter, fluid, bone, tissue. It'll actually get in there with bright enough optodes. So we often will put optodes all over, and we can measure the oxygenation in different regions of your brain. As you think on something, that area of your brain is going to demand more oxygen. So the blood vessels will expand a little, give you a little more blood flow in there. And that changes the amount. So we can actually see where you're thinking in your brain by seeing the oxygenation changes. My interest is on doing this for monitoring and surgery. How do you make sure patients are safe, like when cardiac bypass? People have been doing this type of stuff since the 70s. We're looking at trying to do some advanced stuff to figure out how to do better interventions and things of that sort. So we can monitor in a large area of the brain to try to help during open heart surgeries to be able to protect the patient's memories and basic functionality. And that's all done by this same exact technique. We just have a whole bunch of them spread all over your head. And when we do it that, and we're trying to figure out how a particular area goes by having a large number of them, we just put an F in front of it. So it becomes F nears. The F is lowercase and it stands for functional. So this is functional near infrared spectroscopy, FNIRS. So that's a kind of an interesting area. It has a lot of applications, particularly for surgery or brain monitoring, things like that. Nice thing is, unlike functional MRIs, it's small, it's portable. You can actually put it on people remotely. So it's sometimes used to measure health of like football players if they've got a concussion or something of that sort. So FNIRS is a neat research area as well, all based on the same exact theory going on here. We monitor the same stuff and we care about, is the brain getting oxygenation in the areas it needs to get oxygenation in. That gives you a quick overview of the spectroscopy end. Anybody have any questions on NIRS or its application to functional NIRS or muscle-based NIRS or pulse oximetry to measure blood? All right, well, seeing no questions, I'm going to say awesome. Glad it all made sense. So this coming tomorrow and Thursday, I'll just make a quick note to all of you. We've been, part of what's also been a little bit of a time grab for me has been, I'm in charge of all the candidates coming in. So I have to handle all of their video stuff basically all day, 2 days a week for the last month. Our last candidate is coming in. So this, we're going to have a kind of virtual talk on Thursday. The person's going to give a sample of their teaching. So if you're interested in that, I'll post a link. So this is a potential clinical professor for the electrical engineering side. So if you're interested in kind of seeing, and seeing if this person is a good match or somebody you think would be a good teacher you'd want to take classes from, I'd love to hear your feedback from them. So I'll post a link in Canvas to all of you as an announcement. All right, any other questions? Okay, seeing none, have a great day.
Have a good day.
Great day. Thank you.
You're welcome.
You're welcome. Thank you for your time.